Okay, hi everyone, and welcome to this talk about annotations and reflection in JDK 8. It's fun to see so many of you here, even though there was a party I heard was really good yesterday. So, my name is Joel. I work in the Langtools group at Oracle. We are responsible for evolving the Java language, among other things. So currently I do work on the Java C compiler. I do work on annotations, reflection, and the javax.lang.model. Before that, I used to work on the JRockit virtual machine. I consider myself sort of a VM hacker lost in language land. But it's great fun. So, first, the most important slide of the day, the important message from our lawyers. So, annotations and reflection. So, we want to make, annotations are a big feature of Java. And in Java SE 8, we are going to make annotations easier to write and discover. And also, we want to make reflection more powerful and easier to use. So, looking back, annotations were introduced in Java SE 5. And since then, they've become a key feature of the language. For example, we have overrides, deprecated and suppressed warnings that directly affects your source code and the compilation of your source code. And also the EE world has sort of come to like annotations. Here's a bunch of acronyms for technologies and projects that use them: JPA, JUICE, CDI, JAX, RS, UMS. Basically, everyone uses annotations, and I think that's fun because I work with them. So, today we have what we call annotations on declarations. And what is a declaration? A declaration introduces a new name into your program. Here are some example declarations. For example, a class declaration introduces a new class. There is a method declaration. That is actually, it's three declarations. It's a method declaration, a method. It's a parameter declaration, parameter. And it is also a local variable declaration. And the last line is actually two declarations. There's a list element, that's a class, and there's a type variable, E. And as you can see, you can annotate classes, methods, parameters, local variables, but you cannot annotate the type variable, even though it is a declaration. Not yet. So the first feature I want to talk about is JSR 308 annotations on type use. With 308, you are going to be able to annotate not only type declarations, as I showed in the last slide, but also type use, seen on this slide. Here are some examples of type uses. We have we have a constructor call, the constructor myObject, that is annotated with at A. We have a cast, cast to at bstring. We have an implements clause, and there is a type variable. And also the last line, there is a throws clause that where you can annotate the exception you throw. And none of these are introducing new names. They're not declarations, but they are type uses. So why would you want to do that? And that's a very good question. So this is perhaps a better example of what you will be able to do. This is actually adding some useful information to the annotations. So for example, you can say that you are creating an internal object, or that the string you're casting to is printable. That might be useful. Or you may annotate that you're implementing a read-only list of read-only T's. And the last one, that your exception is critical. Although that might be perhaps better expressed some other way, but you can anyway. So, why would you want to do that? Well, we see type annotations as an enabler. And it's a little bit like with all annotations. The annotations themselves, they're mostly metadata. There's telling something about your code. It is when you interpret the metadata that that's the fun part, that's the interesting part. So this is an enabler, and what we want to enable is what we call the checker framework, and that gives you the interpretation of these. So the checker framework is a pluggable type system. It lets you, as a user of the framework, develop a new type system proving an interesting or useful property. For example, you could prove that your program doesn't throw a null pointer exception. So you can prove absence of null pointer exceptions. Or you can prove that every time a field is accessed, you are holding a certain lock. So while this is far from proving your program free of concurrency issues, it is still a step on the way of making proving that it is have less concurrency issues. And there is also what we call the regex checker, and that can prove that your regex is valid, and also that you're not using capture groups that you haven't introduced. So here's how you do it. Suppose you have some business logic, and you have a method that's supposed to return an entity, and you want to prove that this is null pointer free. So you use the checker framework, you use the nullness checker, and it says, well, there's this factor method here, and I can't guarantee that it's nullness safe. So you as a developer, you go in, you verify the factor get entity, and you realize that either it will throw an out-of-memory error, or it will return a valid entity. So you as a developer, you know that this is safe. So in that case, you can say, well, I'm going to cast my entity to a non-null entity using this type use annotation. And that allows the checker to continue working and continue with its inference, proving your program is correct. So this is why you need type use annotations in this case. So as an enabler, we also like to give you the ability to shoot yourself in the foot. And in this case, we're going to let you shoot yourself syntactically in the foot. So here's a method. It's basically it's a nonsense method, but here I've annotated it with all the type use annotations I could come up with at the time. And I think this is much less readable. So please don't overuse this feature. The good part is that the checkers framework, on average, only needs 2.6 annotations per 1,000 lines of code. So you actually don't need to add that many annotations for the checkers framework to work. Another small change we're doing is this. This is not longer, well, it is a keyword, but it also becomes valid in a parameter position. A little bit like Python, but that's there itself, and it's nothing to do with validity, but anyway. So, and the reason we do this is that every non-static method has what we call a receiver. It is the receiver that becomes the this object in your function. And once in a while, you might need to annotate the this functions, this object, saying that, well, I know that I am a non-null this. That would be the case anyway, but perhaps a printable this. So this was the best position we could think of for adding that annotation. So, a little bit more about the checkers framework. It's been done outside Oracle, which I think is a great example of you as a community. There's a lot of these pluggable type systems, and the fact that it is shipping outside of the JDK is even a greater thing, because that allows you to rapidly experiment with useful or less useful type systems. And then we can perhaps we can take the most interesting ones and make them a part of Java or Java-C if they're useful enough. Okay, so wrapping up JSR 308. The goal of the type use annotations is to enable the checkers framework. Once in a while, the inference in the checkers framework or similar frameworks, perhaps if you want to do a different one. Once in a while, the inference that the framework uses will not be powerful enough. So we have provided you with type use annotations that let you hint the framework. And for that, we need not only annotations on declaration, but also annotations on type use. And that brings me to the next feature. So when annotations were introduced, it was also decided that you could not have multiple instances of annotations of the same type. So for example, you could not do this, the compiler said. So as a community, wanting to write this, you figured out a way to do it anyway. Basically, this is how most people choose to do it. So you introduce, this is what I call the container idiom. So you introduce a container. It's normally named the same way as the annotation you want to repeat, except it has a plural S at the end. And then in the container, as the value element, you have an array of the annotation you want to repeat. So you put your repeating instances into the container. And here's another example. I think I stole this from the EE world somewhere, where you have multiple schedules. You want to write them one way, you're forced to write them another way. So we want to allow you to get back to write, or we want to allow you to write repeatable annotations, while acknowledging that there is a huge amount of code. There's many libraries that already take advantage of the existing idiom to do this. So we think it wouldn't be fair for us to just throw out all that code. That's not the way we work. So instead, my colleagues and I came up with a solution that lets you reuse the current idiom while still getting rid of the boilerplate code. So this is how you do it. So you take your annotation type that you want to repeat, and you meta-annotate that with a contained by annotation that indicates the container where you're going to put this. That is step one. Then if you haven't already created a container type, you create a container type, as you can see, it has an array value element that has an array of the same type that you're trying to store, basically. Did that make sense? I hope so. So if you're going to store the schedule annotation, you need to have a schedule array as a value element in your container. And also, you indicate on the container that you are container for the annotation you are container for. Among other things, this implies that you can only be container for one type of annotation, for example. And there are some additional rules. For example, all other elements except this value element, they need to have a default. And also, this circular indication of you as a contained and your container needs to be correct. And the container, it needs to be retained for at least as long as the contained element. Otherwise, it wouldn't make much sense. And this might perhaps be sort of non-intuitive. The target for the container must be a subset of the target for the contained element. And lastly, if the contained element is documented, the container needs to be documented as well. So provided that you create this container and you follow these rules, then javac will do the heavy lifting for you. So when we find, you can write code like at the top. You can just repeat your instances of your annotation, and javac will, under the hood, synthesize the container for you and let you get rid of the boilerplate, basically. And at the bytecode level, this will look exactly the same as if you had used the previous idiom with the manual container. So the byte stream emitted will be identical. And this is one of the things we tried to do in order to make the existing libraries that use this just continue to work without no modification. And this has been in the Java 8 prototypes for a while, the compiler side. So you can try this at home. It should work, I hope. If it doesn't, please file bugs or email me and I'll file bugs. But we're fairly certain it works. So, adding reflection to this. So you might think that since we are reusing this previous idiom of how to do things, adding reflection should be really easy, right? It turns out not to be. So here's a little aside. Since I work as a language implementer and language designer, and I want to do that as good as possible, I realized that I need to have certain rules for how to evaluate the proposed language change. And I think all my colleagues, we have rules for this. They may be explicit or not, but these are mine. So the first rule is that non-users of a new feature should not suffer at all. And I think this is pretty fair. I mean, if we introduce a new feature that you're totally uninterested in, then it shouldn't be a burden for you that we do that. You should just be able to ignore it. So I think this is a good goal. The second one is that users of a new feature, they shouldn't say, what? And by that I mean it should be intuitive how to use a feature, and there should not be sort of hidden complexity and unnecessary corner cases. I think most of you will agree with that one as well. And the third rule, third rule is that backward compatibility matters. And even more so in a language as big as Java. I mean, there's a gazillion of Java source code out there, and that makes it even more important for us to not screw things up for you. And in this case, I also am a strong believer of that you are Java programmers and not bytecode programmers. So even while it is more like a fact that core reflection offers a bytecode, a class file view of the world, that is mostly not what you're interested in. You're writing Java source, you're looking at your screen, looking at Java source. When you're using reflection, more often than not, you want to see as close as possible a representation of your source, not of what is in the class file. That is my belief. So we already have a couple of places where we differ. For example, retention. That runtime retention isn't the default. This has hit me a lot of times, actually, and I work with this. I work with designing features for this, and still, once in a while, I run reflection on something, and my annotations aren't there, and I'm like, what? So I think we should try, if possible, we should try to lessen or that gap between the reflective world and the source world. So, assuming we didn't do anything with reflection. So here's your action class. It's annotated with a schedule. You want it to be run today. And here's your reflective call. You do action class get annotation looking for schedule. As expected, you're getting a schedule, an instance of schedule today. So adding a second schedule tomorrow to your action. You're doing the same reflective call, action class, get annotation, looking for schedule, and you get null result. Duke says, what? And I call this adding one more schedule should not lose your schedule. I think this is a good example of the source reflection gap. It is there in the source, it is not there in reflection. This is a bad thing. So here's the explanation. So when we only have one schedule on the class, the bytecode basically looks like this. You have an array of an instance of an annotation schedule with a value today. So when you do get annotations, you look in that array and you find the schedule and get annotation, and it returns the schedule. Very simple. Well, when you add a second schedule, and maybe you can guess what goes wrong, there is no more a schedule in the array. There is a schedules that contains the schedule. And so when we go looking for the schedule, sorry, without S, we can't find it. And therefore you get null as a result. And yeah, as I said, I think we think this is quite bad. You have schedules in the source. Oh, sorry. Yeah, you have multiple schedule in your source, none in reflection. This is a bad thing. So the solution is to unpack the containers. And so when you do get annotation or get declared annotation with a specific annotation type, if you can't find any, go look at that annotation. I'll show you. So on the left here is the annotations. Here's how it looks in the bytecode. So you're doing get annotation, looking for schedule class. Since you can't find any schedule directly, you go look at the annotation type of schedule. You see if that is annotated with this contained by. In this case, it is, indicating that it has a schedules as a container. So since you couldn't find any, you go look up if you have any schedules in the source. No, sorry, in the array of annotations. And in this case, you do. So you unpack the schedules and take the first one today. And this is much better, we think. But we're still not really there. So the same example, you have a schedule, except this time you do get annotations unqualified. You just want all the annotations. And this will give you back an array of one instance, a schedule. And as you can probably guess, you're adding a second schedule, and the array you get back, it doesn't contain a schedule, it contains the schedules. And this Duke again says, what? He doesn't like losing his schedules. And again, this is the source reflection mismatch that I'm talking about. So the solution again, you unpack the containers. So and this example is slightly different, but it's pretty much alike. So you have two containers. No, sorry, you have two schedule. This is how it looks in the bytecode. So when you call get annotations, wanting all annotations, sorry, or get declared annotations, we iterate over the returned array. And for every annotation in that array, we look up the type of that annotation, and we see if that is a container for something. So in this case, we find the schedules. We look at the schedules, the declaration of the schedules type, and we see that it is a container for schedule. So we unpack the schedules, and we insert it to schedule it contains. So basically, this gives back the source as you see it in the source code. So here's some updates we're going to do to annotated element for this, and I'll get into every one of them. So first, we are adding get declared annotation, taking a specific annotation parameter. So if you recall that most of the time, annotations don't get inherited. Fields, methods, packages, interfaces, constructors, they don't inherit annotations. But for annotations on classes, they may be inherited if you annotate your annotation type with inherited. There's a lot of annotations in here. So what we do, so we're adding the get declared annotations that allows you to ignore inherited annotations when you want to look at a specific annotation. So looking at this matrix, this wasn't available previously, and it seems more like an omission than anything that we wouldn't want to do. So the next thing we're doing is we're adding get annotations with a plural S for a specific annotation type, and get declared annotations with a plural S for a specific annotation type. And these are the calls we expect you as a library writer to use when you are using the Repeating Annotations feature. This is what makes most sense to use for you. And I'll get in a little on how they work. So I think you can guess the result. They return an array of all the instances of the same type that you requested. So here you have one today, and you request get annotations for the today class, no, for the schedule class, and you get back an array of one schedule. And in the repeated case, when you have multiple schedules, when you request, when you do get annotations for schedules, you get an array of all the schedules. So it's basically like a filter on the unqualified get annotations. And I think, yeah, as I said, I think this is, writing libraries with this, I think this is where you want to, mostly what you want to use. So I wanted to get in a little bit about testing. So we need to do testing even in the core language and the library side. So for this feature, a colleague of mine, Sonali, has been working on combinatorial tests. So, for example, I mentioned that you have a requirement on the target of the containee and the contained. So we go in and we generate all possible sets of combinations of targets, and we compile them and make sure that the ones that are valid compile, and the ones that are not, they don't compile. So this is what we call combo testing, and this has turned out to be useful because there are some subtleties in the target semantics. For example, annotation type is a subtype of type for the target enum values, and that I made a couple of bugs in there, but we found them and I fixed them. And also, of course, we do unit testing, and there's going to be spec tests to this, since this is going to be part of the Java standard. Right. Wrapping up repeating annotations. So the goal is to allow you to write less boilerplate, and while still making sure that the existing idioms of that you have already used for so long remains compatible and useful. So the way you do that is you annotate your annotation types with container information, and then Javac will do the transformation for you, allowing you to get rid of the manual containers. And we updated reflection to better match the source view instead of what is in the bytecode. So this leads me on to runtime javax.lang.model, which is a new feature we're working on. So how many of you have used the javax model APIs? Oh, not that many. So this is my favorite API. Come on, guys. But seriously, this is a great API. You should all use it more often. So, you know that we have multiple reflective APIs in the JDK. I can think of at least 3. We have core reflection. That's what most people think of when we speak of reflection. We have the language model, and I think there are some stuff in the beans on the beans side, perhaps more recently of recent notoriety, perhaps. So I'm going to focus on core reflection and the language model. So core reflection, it lives in Java Lang reflect packages, plus some additional bits and pieces, like Java Lang class, for example. The language model, it lives in javax.lang.model element and javax.lang.model type. This is perhaps why you haven't used it, because the package name is so long. Core reflection is runtime only, while the language model is compile time only. As I've said, core reflection is mostly a class file view, which more often than not perhaps corresponds to the source view, but sometimes it doesn't. The language model is perhaps not surprising, a source view of your code. So core reflection is also low level. It isn't allowed to have dependencies outside of Java Lang, as I understand it. So for example, you have arrays as containers. You don't do lists. You don't have maps. You have arrays. And we all know arrays don't play well with generics, for example. While the language model is high level, and it has visitors, and I love those visitors. I'm going to get in more to that to those further on. So also the language model is very easy to extend. I'm going to show you some examples of what you can do with it. Currently, the language model is mostly used for annotation processing. Annotation processing lives in JavaX annotation processing, and it is the main client. Currently, actually, it is the only way to get into the language model API, but we want to change that. So, looking a little bit at core reflection. Core reflection is, from my perspective, it isn't perfect. So, for example, it uses arrays instead of collections, and well, that you get into trouble with generics, and also they're a pain to print. Having to make an array list of your array every time you want to print the contents. I think that it's unnice. And also, core reflection has, well, it shows that generics were added late in the game. For example, you have get return type, and you have also get generics return type. And the whole API is sprinkled with these differences between the pre and the post generics world. Also, there are a lot of strangeness in the APIs. For example, on every instance of a class, you can call getComponentType, which is only semantically interesting for a class. No, sorry, for an array instance. For an instance of an array type. But the call is there on every type. And also, suppose you are a nested class, you're an inner class somewhere, and you want to find out your enclosing lexical scope. So you call, and here's where it gets weird. So depending on if you are inside a method, you need to call getEnclosing method. If you're nested in a constructor, instead you have to call getEnclosing constructor. And if you're an inner class, you call getEnclosing class. Why not just say getEnclosing element and give you the right one? So there are small pain points with using reflection, and I've had to write a lot of reflection code recently, and well, you get the job done, but it isn't perfect. So here instead is an example of the language model. So this is almost runnable code. It's slightly abbreviated, but not by much. So suppose I want to do anything, I want to do something specific with all the parameters in my code base. And and for me as a language designer implementer, this is something I actually do a lot. I will get into more examples of this, but I need to ask a lot of questions about source code. So I think this might be the reason that this is my favorite API, because it allows me to do this. But suppose you want to do something with each and every parameter in your source code. So you just extend element scanner 8 if you have Java 8 source. You override visit variable. You find out if you're looking at a parameter type of variable, parameter kind of variable. And if you are, then you go do useful stuff, and then you continue the iteration by calling your super visit variable. I think this is really easy, and I think it's a little bit like if you saw Joe's talk 2 days ago about lambdas. This is more like, this is internal iteration compared to the reflection part, which would be external iteration. You have to have nested for loops, iterating over all your classes, iterating over all your methods, iterating over all your parameters. It can be done, but this is a much nicer way. So, I want to talk a little bit about the API. You have the basic, I would say the basic element in this API is named element. Surprise. So an element corresponds to a piece of a source code, a source element. And now that I think of it, we seem to be naming everything elements in this talk, and they're not always the same thing. But this type of element, it corresponds to a piece of source code, a source element. So, for example, a class, say list. The text for class list would be a source element. And there's also the type mirror part of the API, and this corresponds to types. So, if you see the class file source of list as the element of list, then you can see the instantiated type of list. For example, how should I? So, type mirrors allow you to talk about lists of string versus lists of integers versus raw lists. So this type mirror gives you the utility and the abstraction to talk about different kinds of instantiations of the same list. And there's the util part that has a lot of utilities. For example, those visitors that I love. There's a type visitor that you can just extend that visits all the types in your source code. And there's this element scanner that visits all the source. So here's an example of the things that this API provides for you. And it has to do, it is reasoning about overriding. So you have a class A, it declares a method M, and you have an interface B, it also declares a method M. And then you have C. C extends A, implements B. So, let's, how many of you think that A.M implements B.M? Not a single one of you. 1, 2, okay. So most of you would agree that, or would say that A.M does not implement B.M. Okay. So the answer is, it depends. So if you ask the question, does A.M implement B.M as viewed as a method on A? Well, of course, the answer is no, because there is no relation between A.M and B.M. But it's also the case that when you call C.M, the actual method that is going to be called is going to be A.M because of inheritance. So the same method, when viewed as a method on C, is actually implementing B.M. And so this overriding is tricky, and having to write this code in reflection is non-trivial. So we want to do it for you. So here's another example of things I've done with the language model. So I once had to calculate the size of all unique parameter names per class file. So sum up the size of all parameter names in a class file, in all the class files, over all of the JDK. And while many of you are able to ask all the questions you need to be to ask about your project in your IDE, I find that the questions I need to ask about our source code, the IDE can never provide me with an answer. So I wrote a visitor. I think that's the visitor I used for the previous example. And you just sum the parameters, basically. It's really easy. I also had to do an index of all interfaces in the JDK being implemented keyed by class. That you can find from your IDE, I suppose, but you don't get a sort of a nice long data file dump that you can then do regular expressions over and whatnot. Also, at one time I had to calculate the average arity of methods in the JDK, and that was also really easy using this API. So, we currently use this for annotation processing. So you use the annotation processing is the key user of the language model API. And so the observation is that there is a need to do annotation processing at runtime. Take, for example, you have transactions. You don't know which container you're going to be running in. You don't know how that container is going to implement transactions. So the actual implementation of your transaction code, that needs to be done as annotation processing, and it needs to be done at runtime. And so we have the situation where we have two tools for the job, and the better one is not available at runtime. And so, of course, we want to change that. And that is why we're doing the javax.lang.model at runtime. So what we're working on is we will give you this nice set of visitors to extend, the utilities to query about source code, for example, overriding and hiding, and utilities to query about types, for example, generics, bounds, wildcards, and subtyping. All this we want to provide for you in this API at runtime. So we have created a feature-complete first draft, which, as all first drafts, we expect it to change. We're not ready to give it to you just yet, and also we don't really know how to do that yet, but we're working on it. So currently, what you do is we have a factory method that gives you runtime model elements or runtime model objects from core reflection objects. So here are two examples. I'm getting a type element, and I'm doing that by calling this factory create mirror on a class instance. Also, I can create an executable element that corresponds to method by doing create mirror on a reflective method object. Currently, there's no hooks in this for annotation processing or for the JAVAX tools, but we will figure that one out as we go along. And also, this must be like the 10th time I've mentioned those visitors. Must be there. I really like them. Those work out of the box. You can just plug your runtime model objects into the current model utilities, and it just works. And I just wanted to briefly touch on testing for this as well. In this case, we also done a combinatorial testing approach, and also since we have a source time API or source time implementation, we can do comparison testing of this, making sure that the runtime model and the source time model gives you the same results. Except, so what do you do when the information isn't there? And of course, there's not much you can do except sort of accept defeat. There are going to be cases when the information in the class file just isn't there to give us the information that you have at source. For example, in the source language model, the default view of an annotation in the source language model is that it doesn't show you defaults. You have to explicitly ask for defaults. And I think this is pretty natural, because when you look at the source code, if you just glance at the foo annotation, you don't see the defaults. They're not really there, because your eyes work in a lexical way. So I think it's a quite natural choice that the source view of this also ignores annotations. It doesn't matter that this foo annotation has a default in its declaration. It's somewhere else. But there is currently no way for us to distinguish between default values and non-default values from reflective objects in runtime. We can hack the VM to do that, but it's a big job. So there are going to be differences between the runtime view and the runtime model and the source model, but we try to minimize them at least. So here's an example, Prettyprinting. I wanted to print the annotated element. That might not have been a good class to choose from, because there's a lot of elements here. But so I'm creating a javax.lang.model element E using this create mirror from annotated element. And then I get the elements utility, naming again, and that gives you that utility allows you to prettyprint elements. So in this case, I expect to get a output or a printout of the annotated element. And those of you that are, you might notice that this is the old annotated element before we updated it with new methods, and that's correct. Also, you might be able to spot a bug or two here, or just erasure at work, because this is supposed to be a bounce. So either made a bug, or I probably made a bug here. And here's the overrides example. You have a.m, you have b.m, and you want to see if they implement each other. This is how you would do it. So you create an executable element from a.m, called a.m, from the method a on m. You create an executable element b.m, I call it, from the same method b. And then you need to create the elements for the classes, because as I showed you, the implements or overrides, it's not a meaningful question to ask if you don't have a sort of a type perspective. So you create two elements from the perspective you want to see, and then you just ask, does a.m implement b.m as viewed from A, and does a.m implement b.m as viewed from C? And fortunately, the result is as expected. I ran this on my computer just a couple of days ago, and it gives the right result. So this would have been much more difficult to write in reflection. If you need to ask these kinds of questions, using the language model API is a much better tool for the job. So, wrapping up the language model. We, and I especially, think this is a great API, not just a good API, it's a great API for talking about Java source. Unfortunately, it's only available at source time, and we are working on changing that, so we want to make it available at runtime as well. And unfortunately, there are too few of us, so we haven't been able to finish this just yet. We don't know how we're going to deliver it to you, but we are working on it. Stay tuned. So in general, you can find all of the annotations and language features we're working on. You can find more information in our JEPs. So we publish JEPs when we start working on this. For example, this was JEP 120. You Joe Darcy must have posted it, I don't know, 2 years ago, 1.5 years ago. Also, there's a discussion list for enhanced metadata, where we discuss these specs and improvements. And of course, the type use annotations work, that is under the JCP, so there's a JSR for that. So wrapping up, as I said, annotations and reflection are key pieces of Java technology. In Java SE8, we want to make it easier for you to use annotations, to write annotations, and to discover annotations. And it's the same thing with reflection. In SE8, we will make reflection more powerful and easier to use. And I think we will continue to work on this and bring even better annotations and reflective features. And with that, I'm happy to take questions. Right.
Can you put annotations on return types? And if so, how would that work if you also put an annotation on a method?
Come again?
So can you put an annotation using JSR 308?
Right.
Can you put an annotation on the return type of a method?
So the question is, using the annotations on type, can you annotate the return type of a method? I think you can, but I am unsure how. So as I said, this is the 308 part has been done outside of Oracle. I am helping out with integrating it into our compiler, but I have not been part of the expert group. So I have to say I don't know. Yes? Sorry? Right. So the question was how to see what has been generated by annotations and how to debug it. And I guess that depends on what you mean by generated. So I look at when I work with this, I look at the bytecode stream. So I look at bytecode. As I said, I come from the VM area. Bytecode is nothing strange. I even miss working in hex code once in a while. But as if you want to debug what's been generated by the annotations, well, I guess that depends on the code generation framework that you're using. And, well, I can't help you with that. But did I understand your question correctly? Okay. Yes?
Regarding the lang.model API using it at runtime, you won't be able to get the generic types, right? Since there is a type eraser.
So the question was about the runtime model and generic types. And that is actually, that is not entirely true. So it is true that if I look at the list, object on the heap, there is no way to determine if that list object is a list of strings or a list of objects. That does not entirely mean that you don't have generics information available at runtime. For example, you have generic signature in the bytecode. You have there's a lot of generics information as metadata in the bytecode. So you can actually, if you have a method that returns a generic type, you can actually get that generic signature from that method and create a type element that isn't erased, even though you couldn't be able to do the same just looking at the heap. But yes, we do run into some problems, so we don't have the complete information set, but actually we have more than what you would think. Okay, that seems to be all. Thank you for coming.